we are given an array of coin denominations and a target amount. Our goal is to return the fewest number of coins that sum up to that amount. If it is impossible to form the amount, we return -1. For example, with coins 1, 2, and 5 and an amount of 11, the answer is 3 because 5 plus 5 plus 1 equals 11. A naive recursive approach tries every combination of coins for every subamount. This leads to an exponential time complexity because we recompute the same subproblems over and over again. We need a way to store results so we do not repeat wasted calculations. This problem fits the unbounded knapsack pattern, where we can use each item multiple times. We will use dynamic programming with an array to store the minimum coins needed for every value from 0 up to the target amount. Let us trace the array for amount 11 with coins 1, 2, and 5. We start with dp0 equal to 0 and all other entries as infinity. When we process coin 1, every index I becomes I because we can just use ones. When we process coin 2, we update indices like 4 by taking the minimum of its current value or dp2 plus 1. Finally, for coin 5, we check if using a 5 reduces the count for 11 by comparing dp6 plus 1 against the current dp. We create an integer array of size amount plus 1 to store the minimum coins for each subamount. The extra slot handles the target amount itself at index amount. We fill the array with a value larger than any possible answer, such as amount plus 1. This acts as our infinity sentinel to indicate that a subamount has not yet been reached. We set dp0 to 0 because 0 coins are needed to make an amount of 0. This is the base case that allows all other calculations to build upon it. We iterate through each coin denomination in the outer loop. The structure ensures we consider the effect of adding one specific coin type across all possible amounts. The inner loop runs from the current coin value up to the total amount. We only start at the coin value because we cannot use that coin to form a smaller amount. We update the current cell by taking the minimum of its existing value or 1 plus the value at index I minus coin. This step decides whether including the current coin yields a better solution than what we already found. Finally, we check if the value at the target index is still greater than the amount. If it is, it means the amount was never reached, so we return -1. You could also solve this using breadth-first search on a graph of amounts. Another alternative is top-down memoization with recursion. However, the iterative array approach is generally more space-efficient and easier to implement. The time complexity is order amount times n, where n is the number of coins. We visit each cell in the dp array once for every coin type. The space complexity is order amount because we only store the dp array. Remember that unbounded knapsack problems allow infinite items and require building up from a base case. Code this pattern yourself to master the technique of minimizing values in dynamic programming.